Tonight we have MagLab chemist and extraordinaire scientist Amy McKenna, who's going to talk to us about the nature of one of, I guess, Earth's most complex substance, which is crude oil. She has been tackling some of the most gnarly problems involving petroleum, like plugged up pipelines, for many years, and she recently, since about 2010, after the Deepwater Horizon oil spill, began to put some of her incredible skills to work for researching the samples from the oil spill in the Gulf. So Amy, take it away.
Don't clap yet, we haven't gotten started yet. So, well, thank you, Kathleen, and thank you to everybody for coming out tonight on a Tuesday. And so I'm going to make this pretty casual. So this is a real hot topic. Everybody has an opinion about the oil spill because we're so proximally located to the Gulf of Mexico. I grew up on the Gulf of Mexico. I'm originally from Ohio, but I grew up in Clearwater, Florida, and moved here in 2005 to go to graduate school, got my PhD from FSU, and took a staff position at the MagLab. And so since 2005, I've been studying petroleum and industrial problems associated with them. And then in 2010, when the oil spill happened, those tools were able to be honed towards the environment. And so if you guys have questions, we're going to make this really informal. Everybody have a cocktail and we'll just sit around and talk about oil, because I could talk about it all night. And so what we have up here is a picture, and we're going to go through this a little more in detail. So we've been working with many scientists since the spill happened. A couple oceanographers are here this evening, and so we're going to kind of dive into it at this point. Okay, so this is where we're at. We're at the MagLab. This is the National High Magnetic Field Laboratory. Okay, and so in 2010, we had the Deepwater Horizon oil spill. And so I don't like to call this a spill. I like to refer to it as a spew, because this was not a spill. There was not a known volume that was released. This happened over 87 days. They didn't know how much oil was there, because you really can only estimate the amount of oil that's in a source rock. And so you had this released over 87 days. So this is by far the largest natural marine disaster of an oil release in the United States. And this has been a huge opportunity for scientists to understand how oil degrades in the environment and how it affects the ecosystem. And obviously, I don't have to tell anybody here, we're 18 miles from the coast. So of course, the MagLab and FSU scientists, as well as all Gulf Coast researchers, are interested in knowing what are the long-term effects of this oil spill. Is the seafood safe to eat? Is it safe for us to be going to the beaches? And how long are we going to be dealing with this oil? And so there were 5 million barrels of light sweet crude oil. And if you're not a cab driver in Texas, saying light sweet crude oil doesn't have a lot of meaning to you. But from the refinery perspective, that is the oil that you can make a lot of money off of. It's easy to refine. We're completely depleted of the light sweet crude oil that is over land. Where the light sweet crude oil is buried under 8,000 feet of water. That's the oil that we know how to refine. Oil industries all over the world are struggling with the exact same problems. And so you have this release of light sweet crude oil because this was basically liquid gold. They know how to refine this, but in order to get at the light sweet crude oil, they got to go under 8,000 feet of water. And so there's an estimated 5 million barrels of crude oil that was released. Depending on who you're talking to, it's plus or minus about 1 million. BP claims they recovered about 800,000 barrels of the oil, but they never really knew what they started with in the first place. So we'll be looking at litigation for the Deepwater Horizon for decades. They're still litigating the Exxon Valdez. And so one of the big concerns is it's not if there's going to be another disaster, it's when. Because statistically, we're going to have another oil spill happen in the Gulf of Mexico. That is the most active area of oil exploration in the United States. And it's really the only one that's close and within the United States geopolitical realm. And so if you look up here, those companies that are drilling in Deepwater Gulf of Mexico, there's over 1,800 rigs, and that's the United States. Other countries around the world are also drilling in deep water. Brazil is a big one. They've been all over the news lately because they've got a huge oil field out there that's causing all sorts of production problems. You've got some in Norway out in the North Sea, but by far nobody is doing more active drilling in ultra deep water than the United States. So it's up to us to understand the long-term effects of this oil spill so that we can better address future spills and try and mitigate the impact on the environment. And so offshore oil production is really the only frontier for oil exploration for the United States companies. And so this was published in 2008, and it is the main source of growth for the world's oil industry because, like I said, everything that's easy to get at, we've already depleted. And so one of the big things, if you look at this map, it's real. If you've ever tried to look at how many rigs are in the Gulf of Mexico, it's very difficult to find this information because it's all owned and protected by the companies that lease these canyon blocks. And so this is 1993, and we're looking here off the Mississippi Delta and the coast of Louisiana. And the red here shows you the number of wells and the production of those wells in ultra deep water. And this is 1992, 1993, and we accounted for more than a third of the current world crude output. And now if I flip this over and look at where we're at in 2006 and 2007, I mean, you don't have to be a rocket scientist to see that we're going into deeper water. That's where the oil is at. And so we have to understand how to handle these situations because it's going to happen again. And again, the United States alone, we're the birthplace of the oil industry. We produce the least and we consume the most. And so we have to be able to solve these crises so that we can understand how to better use the oil that we have left. And so one of the things that is pretty unique to a lot of people, how many of you have ever held a sample of crude oil? Know what it looks like? I see a couple of people and 2 of them work for me, so you don't count. So nobody really knows what oil looks like. I didn't know what crude oil looked like until I started as a petroleum chemist at the MagLab. And so when you look at biological systems like yourself, like animals, they're extremely complex. They're made up of fats, they're made up of lipids, they're made up of carbohydrates. They're the most complex. I mean, we're very complicated systems. And then when we all die, when plankton, when bacteria, when marine life die and sink to the bottom of the ocean, they're buried under sedimentary layers. And they get cooked and squeezed for 100 million years at temperatures and pressure in the Earth's crust, and boom, 100 million years later, there's oil. Well, we're taking it out a lot quicker than Mother Earth can replenish it. And so that's where we're getting into an issue where we have to understand the chemistry of the oil that we're producing so that we can better use what we have available. And so the biological diversity that's in all of us, in all of our systems, is reflected in 100 million years of Mother Nature doing her work on it. And so a lot of people don't really know where oil comes from. And it's only been within the past 100 years that they knew that oil had a biological origin. Up until the 30s, they thought it came from a mineral. And so if you look at this slide here, we're showing these are the countries with the largest oil reserves. And very quickly, you can see the geopolitical problem with the Middle East. So if we want to reduce our dependence on foreign oil, we're not getting any oil from Venezuela anytime soon. The Middle East is OPEC driven, so they are continually harnessing the price of a barrel of crude oil. Libya, Nigeria, these are not politically stable environments. The only one that pops up here is Canada, right? So Canada's our friend. So I can say this because some of you probably seen Canadian bacon. Whenever I say it to the college kids, they look at me like a blank face. I'm like, remember Canadian bacon? Canada's our friend, right? And so they have a lot of oil. They have 3 trillion barrels in place, more oil than they have in the Middle East, but it's not the same kind of oil. And so what I have here, and I'm going to pass these all around to you guys, I'm just going to take a second and let you look at some of the different kinds of oil that are out there. And so what Canada has a lot of, they call it the oil sands. And so this is like a semi-solid form of petroleum. It's very close to the surface, so they mine it in open pit mines with huge dump trucks. They have gigantic Caterpillar tractors that can hold the equivalent of 700 Ford Explorers in the back. So they're mining this stuff at a very rapid pace. But it's not very efficient because the oil that you get is a very low grade. It's got a very high viscosity to it, so it's basically like trying to pipe peanut butter through a straw. How are you going to suck peanut butter through a straw? You're going to have to either heat it up to reduce its viscosity, or you're going to have to mix it with something. Where do you get the energy to make that heat? Well, you burn a fossil fuel. So you burn a fossil fuel to produce a fossil fuel. So it's not very good quality. And so what we've been trying to do, and what I've been working on, my whole dissertation was spent studying the Athabasca oil sands, which are an environmental disaster, to say the least. And so I'm going to pass some of this stuff around. I'm going to give it to Kathleen so that you guys can kind of feel it. Everything's taped up with electrical tape, so let's not try and open it. It won't do you any good. You can't put it in your car. And so there's the mixture. That's the oil sands that is coming around here that you can see that there's like a solid in it. There's clay. And the part of oil that comes out is called bitumen. And this is a very high viscosity oil. And this is not going anywhere. This is the stuff that you get out that's like the viscosity of peanut butter. And I'm passing around a couple more of these so that you guys can see some of the things that we've been working on. So what we want is this one. It's got light crude oil on it. We want stuff that we can pipe through a pipeline very easily. That's going to be very easy for the oil companies to refine. This is what we don't have left. This is BP's Deepwater Horizon oil. I've been working on this oil since 2010, April 22nd. 2 days after the rig blew up, I was in Houston when that situation happened. And so you can see the difference between what we want buried under 8,000 feet of water and what we have left that you're not going to be able to produce very well. I'm going to pass around another one to you guys. There's some more Gulf of Mexico crude. So even though they look the same though, they're all very unique. Every oil is different, just like every individual is different. And so what we have here are some other things that happen. When you refine oil, in order to get it out of the ground, they basically have to disturb the equilibrium. So if you think about like a sponge soaking up water, that's what a source rock is. And they sink the reservoir pipelines into that sponge, but you need to squeeze it, and there's no big giant hand to squeeze. So they use water and eject water into the source rock, and that displaces the oil. But now you've got water that's mixed with oil. What are you going to do with it? Are you going to dump it back into the environment? You can't do that. They do in the Gulf of Mexico. In Canada, they do not. In Canada, they have a zero discharge policy. But there's two sides to it. You don't want to lose, the oil company, there's a lot of money in this. You don't want to lose the oil molecules that have gone into the water, and you don't want to perturb the water, the dissolved organic content of the molecules that were in the water in the first place. And so produced water characterization has been a huge thing for our research group in the past couple years. And so that's coming around. So a lot of the things that I end up getting on my desk until the Deepwater Horizon sunk are these horribly nasty deposits that they chunk out of the pipeline. And so we're passing around some of these. If you can imagine, if you've got this built up in your pipeline, you're not going to be able to get very much oil out. So they need to understand the chemistry that forms those deposits so that they can predict the behavior. And if you imagine you're sinking an oil rig under 8,000 feet of water, you definitely don't want to have a deposit, because you can't just go down there and fix it. It's very difficult. And so here's what we have left. This is just a simple pie chart that shows you what kind of oil do we have left. And we have only about 30% of it in this, what they call conventional crude oil, and that's the light crude oil. That is buried almost exclusively underwater, in ultra deep water, which means it's below 1,500 meters of water. This extra heavy oil, we have about 25% of the global reserves are in extra heavy oil that's got the viscosity of peanut butter. We have the oil sands bitumen, which is this semi-solid form of petroleum, and we have heavy oil, which flows a little bit more so, but still very difficult to refine. And so the reason why everybody cares about this is because you need to understand how to better deal with the oil that you have, because nobody wants to pay $10 a gallon in gasoline. And so this is a picture that was from a long from a long time ago, but I love to show it because he's got the chainsaw. He's ready to cut off his arm so he can get, you know, a gallon. But this is the problem, is if you can't refine the oil that you have left, that's going to be transferred to you and me. Everybody's going to be paying it at the gas station. And so we've been looking at these refinery problems and trying to better understand the oil chemistry of what we have left. And then the Deepwater Horizon spill happened. We've been doing oil spill related research in little microcosms in the lab since 1996. Nobody cared because there was no big push to try and understand the impact that a huge oil spill and a catastrophe like this would make, especially on the Gulf of Mexico. But one of the things that's interesting is that every time there's an oil spill, it seems that there is retroactive decision making that happens within the first couple days. And so how they're going to address the oil spill is done like that. The incident commander made the decision at the onset within 10 days that they were going to do chemical dispersion of the Deepwater Horizon crude oil. Now the dispersant itself is not bad. It is soap. It's in X-Lax. It's in baby soap. It's an FDA approved compound. But what nobody really knows, because there's never been this type of a dispersant application, is that they injected the oil, they injected the dispersant at depth. And you can see here they did some spraying on the surface slicks. And so I want you to keep in mind that we're talking about the dispersant, and we'll address that here a little more in detail in a second. And so the good, the bad, and the ugly, that's what I like to talk about. The ugly doesn't need to be said anymore. The largest thing is the oil slick at its largest covered 28,000 square miles, which is about the size of South Carolina, just to kind of put it in perspective for you. And so every time, you know, in the early stages of the Deepwater Horizon, there's a lot of comparison being made to the Exxon Valdez, because that was the most recent large-scale oil spill. That was actually a spill. But every oil spill is unique. You can't make comparisons between them because every oil is unique. And so decisions that were made in the Deepwater Horizon disaster were obviously directly impacted by what happened in Prince William Sound. So nobody wanted to see black waves washing ashore along the white sandy beaches of the Gulf of Mexico. And so they're 50 miles offshore. What do? If they disperse it at depth, it stays there. And the public and the majority of people basically don't even remember the oil spill happened anymore, because the oil is not, it's not there. It's not in the news media all the time as it was with Prince William Sound. But there's a lot of differences that happened with the Deepwater Horizon oil, and so I always have to put a picture of Clint Eastwood into every talk that I possibly can. Just makes me smile. And so the good, the bad, and the ugly. One of the good things about the oil spill, one of the best things, is that I'm working with scientists I never worked with before. And so all of us have always historically focused in our own little niche and been pigeonholed to only talk to oil chemists and only talk to analytical chemists. And I don't want to take the time to explain it to you environmentalists on what happens. I'm just going to continue doing my research. Well, now suddenly we have a consortia that's FSU-led, that's funded to study the oil spill, and I'm talking to oceanographers, and I'm talking to molecular biologists, physical oceanographers, modelers, and we're all trying to understand the big picture here instead of just focusing on one little portion. So there has been quite a bit of understanding the Gulf of Mexico as a whole because of the money that's being made available as a result of the unfortunate Deepwater Horizon spill, and the bad and the ugly. And so every oil spill is unique. Every oil spill is different because no two oils are the same. And so in the Exxon Valdez, you had a heavy crude oil that was on a tanker that had a known volume of 300,000 liters. It was coming into pristine Prince William Sound. It was very cold, and it was a heavy, viscous oil, kind of like the bitumen that you guys, that's being passed around. Now the Deepwater Horizon happened in April, 85-degree waters in the Gulf of Mexico, and you had a light sweet crude oil that was highly volatile at the water temperatures. So most of it, before anything could even be done by man, was released into the environment. So it went into the atmosphere. And you have an 87-day spill versus one episode with the Exxon Valdez. You also have the type of oil, as I mentioned, You've got a light sweet crude oil, and very important, the Gulf of Mexico has natural petroleum seeps, huge abundances of petroleum that seeps through the ocean floor, through cracks, through natural sources. So what Mother Nature makes, she has a way to remove it. And so there's a lot of hydrocarbon degrading bacteria in the Gulf of Mexico that's their food. They've evolved on geologic timescales to use oil as their carbon source. And so in the Gulf of Mexico, you can look at estimates from anywhere between 100,000 barrels of oil every month are released through natural sources, all the way up to 1 million barrels, because they really don't know how much is there, and there's no real, it's hard to be able to estimate what you really can't see and do it all with seismic. So there's a lot of situations that could have been more beneficial with not having the oil spill happen, of course, but it could have been a lot worse. Could have happened in the middle of winter. And so there's a paper that was done, this was published in about 2011, and this kind of breaks down the comparison to tell you here, there's a lot of differences here between the Exxon Valdez, but there's a lot of similarities also. So Exxon had started doing bioremediation studies about 2 months before the Exxon Valdez happened. They weren't really tried and tested, but then the spill happened, and so they used bioremediation. You might not know what that is. They just dumped fertilizer all over the water so that the microbes bloomed, and so the microbes could degrade the oil for them. And so there's a lot of, there hadn't been conclusive studies because there really is not there's not the push to do it until something happens. And so you've got the largest scale bioremediation, you've got the largest scale chemical dispersant. And the chemical dispersant that they used was only intended to be sprayed on the surface, and they injected it at the wellhead. They basically took the oil molecules as they were coming out of the wellhead where it was spewing, and took these huge molecules and dispersed them. And if you think of Dawn takes grease out of the way, it's the exact same thing. That's what a chemical dispersant is. It's a surfactant, which is just a fancy word for saying it's a molecule that has part of it likes water, part of it likes the oil, and it goes to that oil and water interface and breaks it down. So you took the oil molecules that were already filet mignon, and now you cut it up into tiny little pieces, and you fed it to the microbes, and the microbes gorge themselves. So looking for the results and the long-term effects of the chemical dispersant is something that I know I will be studying this spill for at least the next 20 years of my career. So this oil spill happened 50 miles offshore. So you're also talking about right at the mouth of the Mississippi River, which is the 3rd largest watershed, and it also is a huge pollutant of the Gulf of Mexico in and of itself. And so as we're talking, you guys are looking at a bunch of these different oil samples that are passing around. I'm going to show you some of the things that we've got from that came from the Deepwater Horizon. So these are what we call tar balls. And so this is a mixture of sand. These are what floated ashore, and we've been collecting these since 2010 and tracking how the oil is changing since the spill has happened. And so they call them sand patties. These you can see, look at the date. This was collected off of Chandeleur Island off the coast of Louisiana, and that was in April of 2011, so about a year past the spill. And here's some other ones that are going around. You can see that they're kind of dirty composites that are happening. And so oil is made up of molecules, as I mentioned before, and if you want to understand how those oil molecules are going to behave in the refinery and in the environment, you have to know what's there. And so the only way that you can know what's there is by looking at all the different types of molecules. And as I said, every oil is unique. None of them are the same. So there's lots of different, just like there's lots of different types of molecules in all of us, there's lots of different types of molecules in petroleum. And so now I'm going to kind of just go a little wonky on you here. Pardon me for being the dork that I am. But so this is an oil that came from the Gulf of Mexico, and we called it Smurf blood. And so there's BP Deepwater Horizon oil floating around that you guys have in your hands, and there's also this oil that came from about 15 miles away from the Deepwater Horizon. Totally different. You can just see, obviously, there's something different about these oils because this one's yellow, right? So why do we call it Smurf blood? I can kind of see it happening here right now, but I'm going to show you in a second. And so that was like the coolest thing ever, and we got a call from one of our collaborators that said, and I'll pass this around, that said, oh, do you want to take a look at this blue oil that we found? Nobody cares if it's blue, because the producer's like, we don't care, we're making a bunch of money off of it. But as a chemist, we're like, yeah, we want to look at, we like cool stuff, we want to see cool samples. And so what it turned out happening, and we did this in conjunction with oil industry, as well as our collaborator up in Massachusetts at Woods Hole Oceanographic Institute. It turns out there's a molecule in here that fluoresces in the UV region. So it's called pyrroline. This is the structure of it. I won't go too deep into looking at talking about that anymore. But this one particular molecule, even at very low concentration, fluoresces enough to make that crude oil blue. And that is a function of the molecules and the types of bacteria that lived and that deposited into that source rock 150 million years ago. And so that was one that was really cool, because every oil is different, and it's all a function of the chemical properties of the molecules in there. And so what we do at the MagLab, and hopefully you guys will come down to the open house and you can see it, is we try and understand the chemistry. If you can understand the chemistry of the molecules within an oil, you can figure out how it's going to behave in the environment and how it's going to behave in the refinery. And so the problem is, the same things that cause problems in the refinery cause problems in the environment. Those same compounds that form these nasty deposits that are being passed around are the same molecules that are going to end up on the beach, because they're basically the toughest kids on the block. They're the ones that are going to resist any type of change. And so what we want to do is try and understand, how is this oil going to have an impact on the environment? How is it going to have an impact in the refinery? And so, you know, the oil companies really don't care. We're scientists, we're academics, so we care about the environment and we care about the Gulf of Mexico, but I mean, let's be realistic. It's big oil, they care about money, right? And if they start having negative profits, they're just going to pass that along to us at the pipe. So here's a picture again of some of the other deposits that we've gotten. And so now we've finally been able to take all of these tools that were developed over 15 years to address the problems associated with the oil industry and just shift our focus. Those exact same techniques are applicable in the environmental realm. And now people care. People want to understand what happens to oil when it's released into the environment, and how long are we going to be looking at it. And these molecules are a fingerprint. Every molecule and every oil creates its molecular fingerprint, and so you can figure out if the oil came from the Deepwater Horizon or if it came from somewhere else. And so, like I mentioned, the big thing is that you want to figure out who are the toughest molecules left, because those are the ones that are going to be around for the longest. If we can fast forward 40,000 years, I want to know what's still going to be on the beach. And so the way you can do that is to try and track those changes as a function of time and see how the molecules are transitioning. So there was there's a lot of paparazzi that happened because this oil spill happened in the internet world, which I'm sure some of you are aware of. I'm sure you've all heard about it. But so this is one of the I like to show, and so they had this spill cam. It was this oil gusher that they were recording as the oil was being released over 87 days, and they were trying to be like, look, we're showing you what's happening. It ended up crashing very quickly. I think after like an hour, the whole website completely shut down because it had so many hits on it. And so you have oil that's released at the ocean floor. Mother Nature is the best organic chemist. She's by far the best one I've ever met. And so when you have oil released, there's a lot of different processes that happen. There's not just one thing that happens to the oil. So you've got, as we mentioned, the microbes. You've got biodegradation. They're going to chew on the oil, but microbes are like teenagers. They're only going to do what's the path of least resistance. So if you give them filet mignon that's already chewed up, they're going to eat the filet mignon, and they're going to leave the room cleaning to somebody else. So that's the way I like to think about microbes. You're going to have part of the oil that's going to go into the water, and so you have what's called this water solubility, and so you almost have produced water being created in the Gulf. As we talked about, you have evaporation, and of course you had a light oil, 85 degree water in the Gulf of Mexico in the summertime. So of course there was photooxidation, because the oil that did finally make it to the surface it's been beat up by the microbes, it's been water washed, and it's now being photooxidized by the sun. Part of it also forms these emulsions, which I'm going to pass some of these around to you because I just think these are really cool. And so when you have oil and water, you're going to have a layer on top that's going to be the oil, and the water is going to go to the bottom. Well, this is a perfect sample to show you what an emulsion looks like, because these emulsions are extremely problematic in the environment because they lock up oil molecules in water. And so you can shake this up and it's not going to change. Those compounds are keeping these two different aqueous or water and organic oil phases completely separate. So I'll pass that one around. And so you want to understand, is an oil that's released, is it going to be one that's problematic because it's going to form an emulsion? Is it going to be easily photooxidized? Where's it going to go? And so the first thing that you have to do, and anytime you're doing this, is you have to know what you started with. It's great to pick up the oil along the beaches and characterize it and say, here's what it is. But if you don't know what you started with, you don't really know where you're going. And so that's what we have been doing, is trying to characterize the oil before it was released, establish the molecular fingerprint, and then you can track that with everything, that all the changes that are happening between samples that are collected all over the Gulf. And so we measure the mass of molecules, and this is about as deep as I'm going to go on what we do, and I'm happy to talk about it later. Every single one of you, one of the most fundamental properties of people, because they ask you on your driver's license, is how much do you weigh, right? Because you can tell somebody apart. I mean, I could tell you I'm 110 pounds, but you probably say, I don't believe you. But that's a fundamental property of everybody. They want to know how big you are, they want to know how tall you are, how much do you weigh. It's the same thing with molecules. Molecular weight, or how much they weigh, is critical to a molecule. It's one of the fundamental properties. And if you can measure that mass accurately enough, you can tell what combination of carbon, hydrogen, nitrogen, oxygen, and sulfur, everything that makes up the proteins in our bodies, and how they're put together. So that's what we do. We measure the mass of molecules very accurately. And we take that fingerprint from what we started with, and we've kept that, and we've put it out to the public. If this is our starting point, this is time equals 0. And so now we can take that and shift over to show you what our real scales are. And so if you come to the open house, you won't get to go all the way. We won't put you to work just yet. Maybe in a year we'll make you come down here and do some helium fills. But this is the ICR bay. These are our scales. This is where we measure the mass of molecules inside of magnetic fields. And so this is what we've done all of our systems on. And I just show a zoom in set here on the one in the middle. So we design everything at the MagLab. I'm not going to go super deep onto it. Basically all you need to know is your oil sample goes in here, and that's a really big magnet. And so we take the oil sample and we put it inside of a really big magnet, and we can measure the mass. And you can tell that we built it here because you can always tell home-built systems because there's tinfoil. And there's a lot of cords, and it looks really impressive, a lot of blinky lights. And so we can measure the mass of all the molecules in an oil, and then we can line them all up. And so basically what you have is a spectrum of those masses, of everything that you started with. You can tell the composition of the Deepwater Horizon before it was released. And this establishes the molecular fingerprint of what your starting material was. Now we can start to do something that's going to have real-world implications, because we know what we started with. Now we can see what washed ashore, repeat the experiment, measure all of the masses in the tar balls from various points along the Gulf Coast, and do that comparison and understand how the oil is being changed. And so this is from June 23rd in 2010. That's when the oil reached Pensacola Beach. And so we've been characterizing the molecules after they've been released in the environment. This is not something that we do on our own. We do this in collaboration with several people from the FSU Oceanography Department, Marcus Hudel. So this is a zoom-in set of some of the sand patties that were collected. These were actually collected on Gulf Shores, Alabama. And so the ones that are passing around looked like this. And so this is where we've been trying to establish what happened to the oil that washed ashore, that locked into sand patties. Now here's an interesting thing that I thought is one of the coolest things. We started this about 2 months after the oil spill happened with Professor Hudel, and we're still working on this. This is a huge amount of data and a huge sample set. And so this is Pensacola Beach. And so what Professor Huddle did was he was able to get a permit to take a backhoe and dig into Pensacola Beach. And very, very defined lines you can see here. You see beautiful white sandy beaches, but if you go a little bit deeper, about 50 centimeters, you start to see this bathtub ring effect where you've got oil that's percolated down through various depths. And so we wanted to see how does the composition of the oil that was deposited on the surface change compared to what's percolated all the way down, because there's very different ecosystems on sandy shorelines and different environmental populations. Ghost crabs, for example, will be heavily impacted by oil being buried in the intertidal swash zone. And so this is just a schematic to show you the same thing. So you have oil, it gets deposited onto the beach. You have many different chemical processes, physical processes working. You have waves coming and washing ashore. You have rain dripping down, and the oil molecules actually penetrate all the way down into the sand. So one of the other things we've been looking at is we have many different samples that have been collected from everywhere you can think of. Skim boats, we have beach samples, we have oil samples that were from these burns, these in situ burns. So whenever an oil spill happens, they like to do these controlled burns where they light the oil on fire on top of the water, because you don't want the oil molecules to go into the atmosphere, but it's a lot safer for them to be in the atmosphere because gas is a lot bigger area that they can disperse over. So they always do these controlled burns to try and get the oil from the liquid phase into the gas phase. And so this is a picture here of the controlled burns. But what happens is, same thing what happens in your fireplace. When you burn something, you end up with a residue. And so that exact thing happened. And so we've been working with professors from LSU who had been getting these samples brought in by shrimpers on their trawlers, where they're getting these burn residue samples at the same depths that they're fishing for their shrimp. And so we call these shrimp cakes because I literally have one of these sitting in my desk, and you can see the shrimp's already in there. And so you want to understand, how did you change the oil? Because this is a big deal. How are you going to remediate the next spill? Are you going to just burn it? And is that going to be a worse impact than just letting the oil stay where it is? And so we're all working collectively all along the Gulf Coast to try and understand and mitigate some of these things. And so we can do the same thing with taking the mass spectrum of the burn residue, comparing it to what you started with, to try and understand how that burning has changed the oil. And so that's basically all I have for you guys, but I'm just going to show you a picture. I don't work alone, by far. There are many people who work in the ICR facility at the MagLab. Alan Marshall over there in the hat on the left, he's the director of the facility. Ryan Rogers is the director and basically the first one who started spraying oil into the mass spectrometers, and it took a long time for the instrumentation guys to let that happen, but now they're seeing the benefit of it. Numerous postdocs and graduate students, John Quinn, Chris Hendrickson, Greg Blakeney, are all the instrumentation group, as well as Nate Kaiser, who's all the way over here. And just to show you, and we, as I mentioned, we are funded as part of the Deep Sea research initiative that's funded through the Gulf of Mexico research initiative. Deep Sea is led by FSU. There's several other collaborators that are here, and this is a consortium. It's not just one type of scientist. There's every discipline you could possibly think of that's associated with the Gulf. Woods Hole is one of our sample collectors, and then the MagLab and NSF. And I'm happy to take any questions or anything you guys have.
Sure.
Thank you, Dr. McKenna. Talk a little about the ability to fingerprint and how that will affect you all being expert witnesses in all these lawsuits.
So we are not currently involved in any litigation that has to do with BP, and I hope to keep it that way.
Don't you think you'll be called, though?
No.
Witness?
No. We have had emails between other collaborators get subpoenaed as part of the determining how much oil was actually released, but we've had no, thankfully, direct. I don't want any part of that. We're academics. We study the environment. I don't want to get into any litigation.
Anybody else have a question?
How much similarity is there between the Canadian tar sands and the Pensacola Beach tar sands?
So it's a totally different starting material. So one of the big problems with the Athabasca oil sands up in Canada is it's got a huge amount of sulfur, like 5% sulfur by weight. Okay, and that might not sound as big of a deal, but the EPA mandates that you have very low sulfur, like 10 parts per million of sulfur in gasoline before it can be burned. And the reason why is because sulfur, upon combustion, forms sulfur dioxide, it goes up into the atmosphere, it mixes, and it makes sulfuric acid. So in the Athabasca oil sands, there's a huge amount of sulfur. Very problematic, very, very difficult to get rid of in the refinery and in the environment. Deepwater Horizon oil was light sweet, which means it's very low sulfur. So sweet in oil means it's got low sulfur. Sour is what they call oil that's high in sulfur. Don't ask me why. The oil industry is still puzzling to me. It's very difficult. I mean, they're just talking with oil scientists is very unique. The one thing is that these molecules that are being left are very similar to what is being degraded in the refinery. What's being deposited, what's forming these, what's sticking together and forming these deposits are the same ones that are sticking together because they're instantly attracted to each other because they hate the water. And so they're very much similar in the structure, but the chemistry that makes them up is considerably different.
So I was intrigued by those shrimp cakes. Are there parts of the Gulf where you would not eat the shrimp because of the oil spill?
So the FDA has been testing every piece of shellfish from sessile organisms like oysters, which are the most susceptible, mussels, shrimp, since the oil spill happened. Everything that is going into the food stream, into the population that's being sold on the food market is being tested, and it's extremely low levels. I would have no problem eating any, I've never stopped eating Gulf seafood, I continue to eat Gulf seafood. However, that being said, there are areas of Louisiana that are still closed to shrimping because they're too contaminated. They're a completely different shoreline than they are in Florida. They're salt marshes, and so they're very susceptible to oil contamination. So there are parts where they're not allowing shrimpers to go to get shrimp to put into the food stream. But Louisiana is a very different economic climate than it is here. So people are going to go and they're going to eat and they're not going to worry about whether or not it's safe. But the shrimp and the food that's being sold to the general public is completely safe. And they're testing it very repetitively, and nobody's ever had any levels of anything that has made it into the food supply.
Well, it's a little different question. You mentioned those are the sweet crudes and land's gone, but Texas is having a revival with the fracking. Could you talk about the chemistry of that a little bit?
So we've looked at fracking fluids as well. That's becoming a huge environmental hot, it's all over the news about fracking and the problems associated with it. Depending on where they're doing the fracking, whether it's in Canada or in Utah or in Wyoming, it's going to change the chemistry because it's all a different type of oil. The big problem with the fracking is that if you're going to get these produced water type samples, where is the water, is it being captured or is it being put back into the water table? And so we're just starting to get into dealing with, I have looked at fracking fluids and they have the exact same problems that the oil companies have. They have emulsion formation. They have chemistry that's driving deposit formation, for example. They're not typically doing fracking where they're not going to get, they're going to frack where they're going to get the biggest bang for their buck. They're going to know that there's going to be a good liquid gold type oil there. They're not going to go after something that's not going to make them a lot of money, that's got a lot of sulfur in it, that's low quality. Like in Utah and Wyoming, it's not as big of a deal because the oil isn't as high a quality as it is in Texas. So they're just trying to squeeze as much as they can because it's over land, so it's easier to sink $100 million into a fracking operation than it is to sink $100 billion into an operation in the ultra deep water where if you have a catastrophe, it's a disaster.
They're adding some kind of chemical, aren't they, to break the oil out?
They are, depending, the different companies have different techniques about the fracking and how they're doing it. Some of them use chemistry, a lot of them use steam and hot water just like they do up in Canada.
About the Athabasca oil and its high sulfur content. Is that something that's making export from the U.S. a good idea for those folks who are refining it on the Gulf Coast? In other words, is the attention paid to low sulfur content shared by other countries around the world, or are they burning oil that's much higher in sulfur content?
So that's an interesting question. So this goes back to some work I did in my earlier PhD dissertation work. So in the Middle East, they use huge turbines to burn these low-quality fuels to generate the electricity to drive the oil production and oil refinery operation. In the Middle East, they treat these $100 million turbines like they're disposable. In the United States, they try and mitigate what oil they send to them. So in the Middle East, it's kind of like China. They don't really care about coal-fired power plants. They're not concerned about what's happening to the environment. They're not going to listen to the Kyoto Protocol. We can only do what the United States is, deeming within the realm of our own country. So Canada is very different. They have a zero discharge policy, which means that any products that come from the production of oil cannot be released into the environment. So they have these huge man-made lakes that you can see from space of oil and water that are just sitting in these settling basins. They also remove the sulfur, and they have a huge amount of elemental sulfur that's 4 miles high and 2 miles wide, and they have about 20 of them. And you can see those from space because they don't know what to do with it. In the United States, in the Gulf of Mexico, is very slow politically to change, but we can just take our oil and blow it off of the side of the rig directly back into the Gulf of Mexico. And the oil company response to that is, well, dilution is the solution to pollution. So we've got the Gulf of Mexico, let's just put it all back into there. And there's a big turn in the oil industry since 2011 that's not going to be the case anymore. So the ones that are forward thinking, the companies that are starting to understand the problems, have been trying to mitigate and be preemptive and know that it's going to be coming pretty soon. They're going to have to either filter the water instead of blowing it off the board of the boats, or they're going to have to try and address that. But the United States has very, very defined limits on sulfur. In Europe, in the North Sea, they don't have as high sulfur as they do in the North American area. So Canada and Venezuela, where they have the oil sands, by far have the highest sulfur content. And they've got the most of it, but it's very difficult to refine, it's difficult to upgrade. So other countries are burning oil, but they have their own limitations on what the sulfur content is going to be depending on the refineries in the different countries. Some of them are a lot less tolerant than the United States, Finland for example. But most of the oil that we have all the oil now. In 2009 we switched over from importing more of our oil in the US refineries from Canada. Because Canada's our friend, right? I mean, we're trying to get off of the Middle Eastern dependence on foreign oil, and so you got to go to Canada, which is a lot lower grade, a lot lower quality. So other countries are burning it the same way.
Hi, I like the picture that you showed us with the sand, where the oil had percolated through and collected in a layer. And I'm just interested to think, did you know that oil came from the spill because of its fingerprint? And also, why did it collect right there? It filtered through the top sand well, and was that due to sand density or for some other reason that the oil happened to collect just in that area?
Yeah, so that was a really interesting observation when we initially saw that picture. Of course, it's not just going to stop. It's not going to get to a certain point and just stop and collect. But you have to remember this is in an intertidal swash zone where you have a ton of wave action. You could get a huge amount deposited on at one time. You could have sand being buried, water percolation. You could have they didn't rack as cleanly on one day as they did on the second day, and now they dumped more sand on top of it because they were replenishing the beach constantly. And so the fact that layer sits there is probably more a function of the fact that it's an environmental sample, not because somewhere it just hit a point where it just said, oh, I'm not water soluble anymore, I'm just stopping. And so we've looked at that as a function of depth, and we've fingerprinted that oil back to the Deepwater Horizon. But interestingly, there's samples that, there's a lot to be a lot of oil to blame on BP. Obviously, they had the biggest release, but we have samples that were collected feet away from each other that were put into a jar. One of them is fingerprinted to only be 60 million years old. This one's fingerprinted to be 100 million years old. Deepwater Horizon's 100 million years old, and they're sitting right next to each other on the beach. And so that's been a huge, huge driver for us. We don't tie it back to the Deepwater Horizon until we know that it's got the same matching fingerprint, which is all done through biomarkers, which are these compounds that aren't degraded, and you can look at the ratio and know exactly what oil it came from and what the source was. We like to blame BP for a lot, but we are, realistic about it.
Have you found that the dispersant sped up the aging process of the oil and I guess basically made it look like it was older faster?
So the one issue with the dispersant is that it basically broke up the oil into much smaller droplets, and those smaller droplets are going to have a higher surface area, so they're going to be degraded quicker by the microbes. They're going to be more easily dissolved into the water, and I do think that there is something to be said about the fact that they did do chemical dispersant. It's not going to be an older, it definitely sped up the degradation of the oil, absolutely, because you took something that was the size of a basketball and broke it down into something the size of a ping pong ball.
Sure. I'm going to ask you a question which may be political, but as a scientist, what concerns do you have about the Keystone Pipeline?
But you said the key word there, as a scientist, and so right now there's not a lot of data out there that has been vetted through the scientific community, and that is where it becomes very difficult as a scientist to understand what is the data and what is spin. And I'm not saying that I know the answer to that question right now, because there isn't any data that's out there. There's a lot of publicity on it right now, the same way that there was a lot of publicity when the spill happened, and now nobody's talking about the oil spill anymore. And so until we can get a little more conclusive study done by scientists, not by the oil companies, by academics who, we're not paid by big oil. They don't get to say what oil research we do. They don't get to tell us what our results say. And so until I see a little more validation of the data through the scientific community, I can't really speak about it.
Anybody else have any more questions? If not, we're going to wrap it up this evening. Thank you very much, Amy McKenna of the MagLab. Did a great job.